let's go to the heat.
Right.
Normally in rocketry or rocket engines, cooling is a really big problem. I can't see anything to cool it with like stuff. Normally you use like the fuel. You can't do that because it's
Yes.
solid. Tell me about cooling of hybrid engines.
It's an excellent question. You don't need cooling in hybrid engines. That's a short answer. The reason is that's ablative nozzle. So you have a material which soaks up a lot of heat and then just burns. So that's how. So you have a very hot combustion exhaust coming out. It soaks up the heat, burns, and then just goes away. Right, and that's as simple as that. So that's an ablative nozzle. In liquid rockets, you have a very thin thing, and your combustion temperature is a bit higher, and that's why you need either the fuel or the oxidizer to move around it. So essentially, that's why I said it's the simplest of rockets in a way. It's a big grain of paraffin, big candle, ablative nozzle, and that's it.
And aren't you using, efficiency when you're going to burn the nozzle, because normally the geometry of the nozzle is really important, or is it just a little bit, so it's not that important?
It's not much, because the internal design is also such that we have the hot gases going through the center and not along the nozzle walls. You know what I mean? So we also reduce that as much as possible, because in the end, we also want the nozzle mass to be as low as possible. If you have a very big nozzle, then also increases the mass.
Okay. To produce the heat, you said that we need an oxidizer. You're going to use LOX, right?
That's right.
Okay. I've heard the rocket, some of the founders did before founding HyImpulse, used a different oxidizer.
Yes.
What oxidizer was it? What is the
difference?
Reason in the shift or behind the shift?
That was an N2O, nitrous oxide, the same one used in Virgin Galactic, right? That's a very good oxidizer, because you can compress it and then it liquefies itself, the self-pressurizing oxidizer. But the performance is very bad.
Okay.
So LOX and paraffin gives the highest performance in hybrids, other than using extremely toxic fuels. So this is the safest combination possible. And guess what? It's the same as a Kerolox system.
Oh, cool.
Because the paraffin we use is essentially solidified hydrocarbon.
Okay, so
yes.
I've read some papers, and there was mentioned a term that it's a liquefying fuel. So right. You have like a solid, but as soon as you start the combustion, you have like the heat. So the paraffin gets like liquid.
That's
and
right.
then probably from the liquid to go like gaseous to the reaction, it's not a big step anymore, right?
Yes.
So
you should work for us. You got the concept right. So that's exactly right. So traditional hybrids, which had very low burn rates, which was a classical problem in hybrids, they used pyrolyzing fuel, so the HTPB, which is a binder in solid rockets. When you apply heat to it, it just you apply a certain amount of heat to it, it becomes a gas, and then mix it with oxidizer and burns. What happens in liquefying fuels like paraffin is that you develop a layer of liquid on top of the solid fuel, and this liquid have droplets which are entrained, right? So you basically increase the surface area of the fuel, it burns effectively. Also, you have more burn rate, and this is why it's a much better concept than classical hybrids. So you have very high burn rates. You don't need to have very complex geometries or multi-port, which you usually see. I think if you check the IMROC rockets, we have a very single port, just a cylindrical port, straight geometry, nothing else.
Cool. So when we're talking about ISP, kerosene and LOX, I think it's around 260 or something like this. So you can go to that and even higher.
That's right.
Cool.
So for the first stage motors, our ISP is roughly 280, and then second stage it goes up to 320, and third stage is somewhat similar. Yes.
Yeah, that's like a really good value.
It's similar. It's if you have a very good hybrid design, which we have, you would have almost the same as the Kerolox system.
Cool. So you mentioned it, like the droplets and the surface gets higher. And yeah, I've heard that there have been concepts to do like solid hybrid boosters for big rockets. And the biggest problem was, like you mentioned, to have multiple ports. So you have the surface area to melt down the solid.
Yes.
And here we have this liquefying droplets. And so will the mixing happen in the whole in the combustion chamber, or is it like you have like stages and the combustion happens in different phases?
It's a big chamber.
Okay.
And it's one big chamber. You have the solid grain. The mixing happens as it moves across. And yes, that's essentially so it happens throughout. We don't have segments as you have in solid rockets, so that's another benefit. So it's an extremely simple system in that way.
Cool.
Yes.
So we have like a small motor here. You just said that the bigger motor is the same that you're going to use in the sounding rocket. So this is the motor you're using here at DLR for like testing?
Yes, that's right. So this is really our call it low altitude demonstrator motor. Since we have a small shape, we have a quick turnaround time if we want to do a parametric design analysis, check a certain feature, a certain design which we want to check, internal ballistic structures, etc. We can quickly do it, test it, see if it works, and then apply it on the bigger motor.
So it seems like this is the whole idea, like having this design to do like
it's
reiterative,
like a sandbox or a playground, if you can say that, because in the end, testing the bigger motor is a comparatively bigger process, even though it's a relatively a simple system to test, and we want to shorten the development time as much as possible. So we have rapid design iterations at this scale. And then we are able to select the best one to the bigger scale and test it. Sometimes scalability always doesn't work, but we have cracked it, and that's a big achievement. Usually, when you scale from a lower to a higher system, it doesn't scale linearly, but we've been able to achieve the optimum we want in terms of performance.
Cool. So you mentioned it, testing it. I've heard that the bigger design already had fired.
That's right.
And worked fine. And
worked great.
I saw some videos on the internet. So you've done that on Shetland Islands, I think?
Yes.
Yeah.
So we actually, it was a second test.
Okay.
The first test campaign was in Lampoldshausen. So we tested it last September. We had a series of tests. That was the very first time we were testing the big motors. We were all excited, and it went well. And then we optimized the design further and tested, let's say, the flight version in the Shetland Islands recently, and that was also a big success.
Cool. And where are you going to launch the big rocket, so the small launcher?
Yes, there are many launch sites we're currently in discussion with. One is naturally the Shetland Space Center because of our existing partnership. We already tested there. We know the people there. Of course, we are also open to other launch sites, and we are in discussion with several.
Cool. When we come to cooling, I've been to a mix, or no, I will start it again. I've been to a student group, to HyImpulse, the student group inside the student group that did the small launcher, and they told me that they put a color inside their. They use HTPB and use a color to reflect the heat inside the combustion chamber.
That's right.
Inside.
Yes.
To the middle, so you do not have that much heat to go to the shell.
Yes. paraffin is white, candle wax is white. Then you put a bit of carbon soot in it, it becomes black. So it's able to, so you have the chamber in the middle, and then you have the flame coming across it. We want to trap as much heat as possible inside. One, it increases the burn rate because there's more heat and increases thrust. Second, it protects the outer part from getting too high. We do have, of course, thermal insulation, but we also want to reduce the sizing of it because it also increases the mass if you have this thick thermal insulation. So that's why we usually add black color to hybrid rockets in general to just trap all the heat and increase the burn rate.
Mm-hmm. So I've heard in solid fuels, normally you have something that is left inside the rocket. Do you have the same problem with like hybrid engines? Is there fuel left inside the combustion chamber when the combustion ends?
Yes. So propellant residuals, what we call them, is critical for the design of the rocket. In hybrids, it's less of an issue compared to solids because in solids again you have a mixture of oxidizer and fuel at the same time, so you need to leave a bit as a protection. In hybrids, you actually don't need it. So our design is we leave as minimum as possible and optimize for it so that we don't have the residuals, which adds to the dry mass, which means you have less payload.
Cool. How many people work here?
Now we are around 64. It's close to 60, 64, yes.
And are you going to plan to get some more employees the next time?
We do. If you're seeing this video and if you're interested, yes, make sure you check out our careers page. Our plan is roughly double our size within a year or so. So it's a lot of people to start working on all these subsystems. So yeah, we're going to expand rapidly.
And what kind of people do you want? Aerospace engineers or what?
Everything. I mean, running a rocket project is not just about building it, but also operational, project management, supply chain, media, business development, everything. Yes.
Cool. And so when we talk about time, when are you going to plan to launch the sounding rocket? When are you going to plan to build the big rocket and launch it?
Well, the great news is that the sounding rocket flights is by the end of this year. We have already qualified all the subsystems of the sounding rocket, every single of them. We're just waiting to package it together and then launch it. The maiden flight of the mini launcher, the small launcher, is around 2023. So around Q2 of 2023, that's the estimated timeline.
Cool. Thank you for having me and answering all of my questions. Maybe when the next time you're going to Shetland, maybe you can call me.
Yeah, sounds good. Good having you. Thank you.
Bye.